So here's the last part of this series of talks, generalization of Дэна functions. So let me first quickly recap what we did. So in 2021, so the first one we introduced is called centralized and abelian Дэna function. So what we did is we actually introduced some equivalence class in this equalities we have and simplify the Дэna function so that we can estimate the lower bound easily of the ordinary Дэna function. Also the abelian Дэna function, yeah, I forgot to write Дэna function. Yeah, the abelian Дэna function has a relation to the homological Дэna function, the second homological Дэna function. And the second one we talk about is the average Дэna function. In this case, we basically estimate the complexity, the average complexity of this Дэna function. So we use a random walk model to give the probability distribution to all the words that equals to 1, and we basically take the expectation on this model. The third one and the fourth one is, the first one is the homotopical Дэna function. Which is called G Дэna function of to the k defined for the group of type f k plus 1. So in this case, we basically fill the n spheres with n plus 1 doors, and we generalize this Дэna function to the Дэna function of the space, and we just take some high dimensional space and we allow our group to act on geometrically, and we basically use the Дэna function of the space to represent the homological Дэna function of the group. Finally, is the homotopic Дэna function. Homological, sorry. Which is somehow is called the filling volume function, defined for groups of type fp k plus 1. Okay. For the second, like if k is 1, it is give the upper bound for the abelian Дэna function. So the abelian Дэna function is also a simplification of this homological Дэna function. Anyway, so that's basically what we did from now. So then we the first part of this talk, we will talk about the Дэna function for infinite presentations, and we will talk about 3 different generalizations in this case. The first one, so that's the first topic, the Дэna function for infinite presentation. Actually, we already saw such examples. Is the last one, the homological Дэna function. So, for example, we talk about the second homological Дэna function, which is defined by filling one cycle with 2 chains if the group acts on a space of type fp2, and which is defined for every such groups. And it is known that obviously they are the fp2 is strictly larger than f2. So f2 is a set of groups of finite presentations. So fp2 is a set of group acts on this, or you have the finite second like the projective resolution of this group. Anyway, so basically it's a larger set, and actually this set is uncountable. So this Дэna function actually is the second homological Дэna function defined for uncountable many groups. And also it is very nice.
Vенхао, I'm sorry. Yeah. Can you give an example of infinitely presented FP2 group? Just yeah, I think it would be it would be useful.
I'm not sure if I know a specific one. Yeah.
Okay.
Yeah, the construction is for the some K0. Yeah. Complex.
Yeah.
Yeah, the racks. Yeah.
Okay.
Yeah, I'm not sure yet. I'm sorry about that. But this is the uncountable remaining of this FP2 was proved by Leary, I think in 2008 or 9. This term function is called as a metric invariant, which is behave nicely under the the geometrics wise. But the catch is this group does not preserve this notion does not preserve the solvability of the word problem, which is one important aspect of this ordinary term function. So here is one example given by Brady, Koffler, and Soroko. So they have a group of type FP2 such that it's this secondary second homological term function is n to the 4, but the word problem is undecided. Okay, so that's very unfortunate. And also, what is the relation between this second homological term function and to the ordinary term function is still unknown if G is, so if G is finitely presented and their relation is unknown, it is conjectured that the ordinary term function always gives the upper bound of this homological term function. And it also proved that there is some group such that this homological term function is strictly less than the ordinary term function. So finitely presented group. Okay. So that's basically one portion of the last talk. So basically we already see some term function defined for infinite presentations.
I think free metabelian group of rank 2.
Okay. It's of FP2.
Yeah.
Okay. Good. Thank you. Okay, so now we talk about, so we define the term function for infinite presentation are provided by the work of Bergerchuk and Ivanov. So their idea is we take any infinite presentation and we count the cells in the Van Kampen diagram. So let me expand. So consider we have a group with a presentation, of course. In this case, we assume it is finitely generated because we have to consider the Van Kampen diagram. And we assume this set relators is cyclically reduced. Okay, so if this relator set is a subset of this group G, we do not require it is to be finite. But if this is called decidable, if there is an algorithm to determine if any word in G, so if this word inside this set R for any word in G. So basically the membership problem of this subset is decidable. Okay. So now we briefly recall the Van Kampen diagram. So hopefully you all really know what is Van Kampen diagram. It's a diagram basically simulates the structure of the word in the K2 complex. Okay, so we consider a word inside the normal closure of this relator set. And the Van Kampen lemma says if this word inside this normal closure, then there exists a Van Kampen diagram delta W such that its boundary of this delta W is the boundary of this diagram is freely equal to W. So it's okay. So the Van Kampen diagram basically looks like this. You have a diagram and each cell is labeled by R. So you tessellate the whole diagram and each cell is labeled by R. And the boundary of this is read by the word W. Okay. Now we can define.
R is a set of words.
The words in R, yeah. I
okay,
should
that's
say that.
okay.
Yeah. Every cell labeled by a word in R. But in this case, the R is might be infinite. Okay, so now we define there's a function. So we call the delta J is all J cells of the delta, where J is equal to 0, 2, 1, and 2. So every 0 cells, every 1 cells, and every 2 cells, we count the number of them. Therefore, we define, okay, what is the L sub J of W? W is, of course, is a word inside the normal closure of R. Is the minimum of the size of this set where the label of this diagram is equal to W. So basically it is mostly like the area, but in terms of different dimensional cells. Okay, so that's basically we define the area for a word. And finally, we define the Дэna function. So the Дэna function is defined by, let's call it this way. So the delta of J of N, which is the maximum of the L sub J of W, where W is equal to 1 and W, the length of the W in terms of the generated set. So the X is less or equal to N. Okay, so I have to say the W in G is equal to 1. So it's the maximum number of the J cells determines the Дэna function. So if J, the first observation is, okay, if J is 2 and R is finite, this is basically the same as the Дэna function we talked about earlier. Okay, that's the first observation. The second observation is this Дэna function, this notion, of course, determined by the presentation. So for example, you can include R with all to be the all words that equals to 1 in G. Then the whole thing is basically, so every J is basically equivalent to N. Actually, it is the Дэna function is just 1. The Дэna1 function and Дэna0 function is basically the length of the word. But they are all equivalent to the linear function. So this function basically, if you choose R to be all words equal to 1, basically this notion does not tell you anything. The third observation is, okay, if we have a subset of, so if one of these R prime is a subset of another set of related R, of course, we have to require them to generate the same group. Its normal closure should be the same. Then we have the Дэna function with respect to the R is definitely bounded above by the Дэna function with respect to the R prime, okay, of N. So if you have a lesser words inside R, the Дэna function is presumably become larger and larger. But one might think, okay, maybe we should choose the minimum R to be the optimal choice of relators. But actually, there are groups. There exists groups such that there is no minimum R you can choose. Anyway, so that's the first three observations you can make for this notion. Okay, so let us talk about the results corresponding to this. So as I said, this work is given by the Gorbachev and Ivanov in 2009. So the first is, okay, what is the relation for those like three different functions? So for every presentation, their Дэna function, the Дэna zero function is always bounded above by the Дэna one function. I should use n. And of course, the Дэna two function is also bounded above by Дэna one function. Okay, so these are easy to see if you have a diagram, and this is naturally comes to the relation between the number of 1 cell, 0 cells, and 2 cells.
Okay, can we look at once more at the definition of this delta? Okay, that's
which delta?
Yeah,
this Дэna function. Yeah,
delta J.
Here is the maximum number of J cells in the Van Kampen diagram.
J cells. What are J cells?
J cell. This is you can think it's a CW complex.
Yeah.
And you have 0 cells, which is points. So how many points in the diagram? How many edges in the diagram?
Okay, I see.
And finally, how many 2 cells? Yeah.
Okay.
That's
the number of 2 cells. Okay.
Yes.
Exactly.
Okay. So that's why these results are easy to see. You just look at the number of obviously 0 cells, less asymptotically less than the number of 1 cells. Basically, is you have two times the 1 cells should be bounded above by, the 0 cells should be bounded above by two times the 1 cells. Anyway, so that's the easy observation. And the second result is, okay, so in most cases, the Дэna zero function and the Дэna one function are distinguishable. So if every word, every R inside R such that the length is greater than 1, basically you don't have any redundant generator, right? Redundant element. If this length is 1, basically this whole thing is just trivial. So if you don't have any redundant relators, then we have the Дэna zero function is equivalent to Дэna one function. Yeah. So they are in a sense distinguishable. So we mostly will just talk about Дэna one function in this talk. The third observation is if R is finite, then the three of them are equivalent. So the Дэna zero function is equivalent to Дэna one function, is equivalent to Дэna two function. That's why when the group is finally presented, we just talk about the ordinary Дэna function. If we don't need to care about other Дэna one function, Дэna zero function, and they are all equivalent. So that's pretty nice. Okay, so now, let me just. So since this obviously this function, the notion depends on the presentation you choose, so it's not behave very well under the geometric invariant, but it preserves the computability, the solvability part of this Дэna function. So in this case, obviously, this theorem also given by Gorbachev and Ivanov. If we have the set is decidable, the set of relators are decidable, and of course we assume that every R in R its length is at least 2. Then the word problem of G of this group is decidable if and only if the Дэна function is computable. And also in this case, because we assume this condition, so it's in the same as saying the Дэna function is also computable. Okay, so that's the computability theorem for this this notion. But how about what the Дэna function? They give a counterexample. So there's an example such that there is a finitely generated infinitely presented group G such that R is decidable. Of course, the Дэna function is recursive. Actually, the Дэna function is equal to 2 for every n. So it's recursive, but the word problem of G is undecidable.
So these groups are usually called recursively presented.
Yeah, recursively presented.
Yeah.
Yes. Okay. So basically, the Дэna function does not have such nice behavior. Okay. The next. So there's one more thing about this notion. So the Дэna function actually is something was introduced before, but in a different type of notion. So let me just give you some give here a remark, which might be extended to the more general case. So here, so the Дэna function. So from now on, we just talk about Дэna function. Forget the Дэna function. Is equivalent to the derivation work function. Introduced by Bridget. Okay, so let me just explain what is derivation work function. So if we have a derivation, basically we start with this word W and replace it by V, a one-step derivation where the W inverse times V is inside the set R. So the work of this derivation, U to V is the sum of the lengths of two words. So the sum of U and V. Okay, now we start with an any word W, and if W is equal to 1, basically W in the normal closure of R, we have a derivation of this word to reduce this word into the trivial word, the identity. So here, for example, we call it the W is equal to W1 and W0 reduced to W1 and so on and so forth. Every step, the derivation, for example, for this step, basically we replace a word of type AUB by a word AVB, where U inverse V is inside the set R. And so the work of every step is, the work of any step is equal to the sum of UV. So regardless of the other words A and B.
As far as you can see, the sum of lengths of U and V is just the length of R.
Yes, yes, yes.
Okay.
you're right. But yeah, so here basically that's the work. We only care the part we replace. So regardless what other tails and from the head and tails are. So now we just count basically how much work we did to reduce a word in, to the identity. So we define the work of W21, this derivation, to be the minimum work, to be the minimum work of over all derivations. Okay. Or maybe we just call the work of W. And the derivation work function is obviously the maybe I just write the sum of work of Wi minus 1 to Wi. The derivation work function, what's the notion? Okay, it's a sigma of n is the maximum derivation work of W, where the W of length less or equal to n. So that's the derivation work function. And you can prove this is equivalent to the Дэна function.
Excuse me.
Yeah.
Excuse me for interrupting you. So actually, let me say a few words about this. So there's another view on this. So when we compute the usual Дэna function, so we just count the number of defining relations when we to deduce one to deduce the equality W equals to 1, or the number of two-dimensional cells of one compound diagram, right? But actually, we can generalize this. We can consider not just the number of cells or the number of relations, but we can consider weighted sum of relations. So we can assign a weight to each relator, and in this definition delta 1, this means that we assign the weight which is equal to the length of relator. But we can actually use any function which depends on the length of relator. For example, a square of the length of relator, or logarithm, and so on. So it would be interesting to consider this these different weights.
Yes.
Okay, that's if the weight is constant, then the corresponding net function doesn't relate to the solubility of the word problem, right? But if the weight is linear on the length, is just the length of relator, then it's this we have equivalence. So it would be interesting to consider different functions.
Yes.
For example,
we can even consider probability distribution on the set of relators.
So, but okay, this is nothing more than we assign weights to relators. Okay.
Yes. So from this definition, you can tell this derivation work function is equivalent to the Дэna function. And if you define the derivation length function to be what's the length of this derivation, and you take here the minimum length of this word and take here the maximum derivation length, you get basically the Дэna function. So you have on one side, you count how much work you did. On the other side, you count how much steps you did. Okay, so that's just another view of this Дэna function. So in this case, you can generalize this to, for example, I think Alexei mentioned that for the semi-group, you can also define such notion and count how much work you did to derive a word to 1. Anyway, so here, the next result also related to the computability. Also given by the Gorbachev and Ivanov. They observed that under this definition, actually, it's very easy to see. Okay, if we have a group finitely generated, then the word problem is in NP, so it can be solved by a non-deterministic Turing machine in polynomial time, if and only if there exists a presentation with the same generating set, Sk, and with R, the set of relators for G such that its then one function is bounded by a polynomial, and the problem decides the membership problem of this set of relators. The problem to decide whether W inside this set of relators is in NP. Okay, so you can tell for the then2 function we have, okay, if you have a word problem where the word problem is in NP, you can embed such group into a finitely represented group with polynomial then function. That's the theorem given by Rips, Sapir, and Bridges. Okay, so but this is much simpler. Like we don't have to embed such things, and we can directly derive from this condition. This word problem is NP, and we can know, okay, the then function is in polynomial. It's bounded by the polynomial. Okay, so that's pretty nice. Also, one remark is you can actually replace this NP by, so you can replace NP by the n space, it's capital, yeah, n space, sorry, p space, sorry, no, p space,
p space, okay,
yeah, polynomial space, yeah, you just, okay, so the theorem is still true if you just replace NP by p space. Okay, so one consequence of this theorem here, they actually compute. So since we introduced the notion, and we can actually compute or estimate some of them. For example, they compute the free Burnside group. So for m greater or equal to 2, L is greater or equal to 2 to the 48 odd, or divided by 2 to the 9. And let B be the free Burnside group, BML. Then we have to equate this Burnside group with the presentation. So a specific presentation given by Olshansky in his book. So because the then1 function, then2 function, or then function depends on the presentation you choose. But anyway, so if we have that presentation, you can show that under this circumstance, the then1 function is bounded by n to the 90 over 12. So it's bounded by a polynomial of a fraction, and actually it's lower than the quadratic. So it will be interesting if we can actually prove this is between the linear function and quadratic function, but they only give the upper bound. So the corollary of this, of course, is the word problem and the conjugacy problem for this group is in NP. Okay. So that's I think that's the first part, the first generalization of the for infinite presentations. Let us go to the second one. So it's now we just consider finite generated group. Where so finitely generated. And now we just think about, okay, we approximate the whole group by partial relations. So we define, okay, the set of S sub k are all the words in the free group generated by the set, such that the length of this word, reduced words, is bounded by k, and the element is equal to 1. So we consider all possible relators within the radius of k, of radius k. So we can define a group, which is it's a finite presentative group, which is given by the generating set, and the relator set is just S sub k. Okay, so in this case, we just this group may not equal to, so may not isomorphic to G. If G is finitely presented, it will eventually become G. But if G is not finitely presented, it will just, so the G basically is a direct product, a direct limit of this. So all the GK form the direct system, and you just take the direct limit and you have the group G. Okay. So that's the thing. Then we define okay, a set, which is the subset of the triples of natural numbers. Okay. So we define the what I think is called a multivariable Дэna function. Let me say the multivariable Дэna function, which is a group associated with this, I think, the generating set from these tuples to the triples to the set of natural numbers for finite generated group G, where this set K, M, N is equal to the maximum area. So basically what we did is we consider the maximum area in a subset of this group, or in the sum G sub M, such that this word is in the normal closure of S sub K, and the set W, of course, the length of the word is less or equal to N. So here we consider, so if you look at the definition, we consider words in such set, and we basically see what's the behavior of the words if we increase the number of relators we had. Okay, so we have, because this is definitely not the Дэna function we talk about, and it's not the function from natural numbers to natural numbers, so we have to introduce a new equivalent relation. So for two functions from this triples of natural numbers, if f is asymptotically bounded by G, if there exists a constant, a positive constant, such that the f c m, so we multiply the c to the m. Of course, we want this side is G of ck m cm and plus c times n over m plus c. So that's the new equivalence class, and of course f is equivalent to G if and only if f is bounded by G and G is bounded by f. Okay, so one quick observation: if you look at the definition, if G is finitely presented.
Excuse me,
yeah.
Is it what Katya with
Yes.
Mark are doing?
Yes, it's exactly that.
Okay.
Yes.
So
yes.
we hope that Katya will speak about
okay,
about
so
this
that's the spoiler.
in more detail. Okay, but
Okay.
anyway,
Yeah,
that's just my remark. Okay.
Okay. So let's just briefly just go over all the results they did. Yeah, I don't want to spoil a lot. Anyway, so if the first observation is if G is finally presented, then basically the nomenclature of SK will stabilize after some K, like the K is big enough, K is large. So this basically the asymptotic behavior of this function will not depend on K, right? So it does not depend on K. So here's the theorem. I think it's by Olsen and Rybak. Hopefully I pronounce correctly. If G and H are finitely generated groups, so obviously we define this this equivalence class. We want this you know, the nice behavior under quasi-isometric. So if G is quasi-isometric to H, then they will imply their function under this equivalent class equivalent. The multivariable Дэна function of it. Okay. So as I said, if G is finally presented, the K basically is, so the function does not depend on K. So therefore, one quick example or one quick corollary of this is if G is finitely presented, let G be finitely presented, then let me just write. So the Дэna function, this is the normal Дэna function. So the Дэna function of G m over n of m and of n respectively will give a lower bound of this function. Yeah, it's true. K m n, and the upper bound will give it by the Дэna function divided by n. Okay. So
not by n.
Yeah, not by n.
The Дэna function divided by m.
Yeah, you're right. Yeah. So quick corollary of this, if you have if G is hyperbolic, then such function is equivalent to m over n or n over m. Also, if G is semi-hyperbolic. So basically, the semi-hyperbolic function will have the quadratic Дэna function. Then the G of this is bounded by is equivalent to n square m square. Yeah. Okay. So yeah. So maybe I just reserve some results and we just go to the third part of this Дэna function for the infinite presentation. Okay. So they also have some results related to other class of groups. So just looking forward to her talk, hopefully soon. So the last part, which is not actually a definition for a group, it is actually a definition for a variety, so which is called verbal Дэna function. This notion is investigated by Olszewski and Sapir when they want to study the infinite presented groups. So they study the free solvable groups and they study the free Burnside group. For them,
excuse me, just one quick question for this previous corollary. Yeah. Actually, not for corollary. So, for example, consider metabillion groups, which were usually infinitely presented, right? So, can somebody compute this this multivariate then function for them?
For some abelian groups, it is quadratic. It's n squared over m squared.
Okay.
For every
For free,
abelian
for
groups,
example. For free.
I guess it's quadratic.
Quadratic. Okay.
So n over m squared, but I don't know for any abelian group.
Okay,
so
okay.
I don't know
For
the
any,
answer.
so we don't know, of course. But okay, okay. Thank you.
Let us just go back to the verbal Дэна function. So they define for a variety. So instead of for some specific groups, but you can use this notion to study the free groups inside the variety. So let's see. So that V be a variety that defines by a finite set of rows or finite set of identities defined by a finite set of identities. Then we can just basically multiply them together to get one single law. So then it can be defined, but of course we have to change the index such that every variables in each identities are different. It can be defined by a single law, a single identity. Let's call it V, where the V is x1 to xk, x sub k, from the free group of infinite rank. So this is a free group of infinite rank, and the generator is just x, the capital XI. So that's what we want. And then we just consider the verbal group. The verbal group of this variety is a subgroup of this infinite, the free group of infinite rank, such that, so consisting of all words that vanish in this variety. So consisting of all words vanishing in all groups of the variety V. So so this V be fancier. So this is the variety V. Okay, so that's all the words. And if any words inside this verbal subgroup, it will look like this. So basically it's a product of a conjugates of word of this form V. So basically we plug in different generating set, and we get, so here is from 1 to n. So W will equal to such word. So that's all the elements inside the verbal subgroup looks like. Okay, so basically we plug in all these elements inside this identity and make a product of conjugates of all such words. So now we can define the verbal isoparametric function. So here we have a natural numbers to natural number is a verbal isoparametric function. Of the word V or the identity V, if any word in the verbal group, there exists a, let's call this representation star. There exists a representation like star, such that they choose to estimate the number of the variables you plug in. So number of xij. So in this case, if I is 1, we have x11, x12, x1m, and I is 2, then you just do it. And so we just take the sum of all xij such that this is bounded by, because it's as a parametric function, is bounded by the verbal as a parametric function. But I think in one remark, they mentioned that if you just count the n, so you just take this to be n, should be the same, or the result should be the same. Because of course, this just the maximum number of these variables is k, is already given by the identity. The smallest one is called the verbal Дэна function. The smallest verbal as a parametric function is called the verbal Дэna function. Okay. One remark is, as long as we define the same variety, we don't care the choice of the word v, because you can replace v by v to the n power. Still is the same, it defines the same variety, but we just have another different identity. So under the equivalence class we defined for all the Дэna functions, maybe we call the Дэna function the delta verbal. Okay, the verbal Дэna function does not depend on the choice of the v. Okay. So what is the use of this? So here they have a nice embedding theorem, but first they prove first the verbal Дэna function is superadditive. So our old friend superadditivity. Just a side note. So this function is always superadditive, which let me just remind you, if a function is superadditive, if n1 plus n2, they are all ni are inside the natural numbers, is greater than f of n1 plus f of n2 for function from natural numbers to natural numbers. Okay, so that's a superadditivity. The theorem, Ostrowski and Sapir, they're given by 2000, is that, okay, if we know the verbal Дэna function, we can embed the free group inside the variety to some nice group, finite presented group with some nice bounds on its as parametric function. So let me show you the statement of theorem. So let f of n to be any be the verbal as a parametric function. Of a group variety v. Defined by identity, the single identity v equals 1. Then the free group in the variety, the free group of rank m. So you can just basically plug in any variety you want, can be isomorphically embedded into a finitely presented group. Finitely presented group H, where H depends on the identity you choose and the number of the rank of the free group is. The construction explicit depends on this. So if you know the identity, know the rank, you can just construct the H directly. with an isoparametric function. Equivalent to n square f of n square square. I think that's the result. So now if you know the verbal isoparametric function of a specific variety, you can actually embed all the free groups in the variety into a finite presented group with this bound. Okay, so yeah, what's the consequence of this theorem? First, they investigate the Burnside variety. So let B of n to be the Burnside variety for n very, very large. You can choose according to a method given in the Oshensky's book. You can choose the function to be the quadratic polynomial. So the f of s is s to the 4 is a verbal isoparametric function of b sub n. So now, as a consequence of the theorem, you say, okay, free Burnside group. So free Burnside groups embed of course for n very, very large, so sufficiently large, embed to a group with n to the 18, the polynomial Дэna function, so Дэna or isoparametric function.
Finally presented, of course.
Yes, finally presented. And also they improve in this paper by unpublished work by, let's see what's Mikhailov, which is unpublished. So you can actually replace the verbal isoparametric function by s to the epsilon of s, where the epsilon of s goes to 0 as s goes to infinity. So therefore, you can embed the same embedding theorem. You can embed a finite presented group with an isoparametric function of n to the 8 plus epsilon of s. Okay, so that's some very nice example, because on one side you have very basically torsion group, very torsion group inside this. So that's their method. But last year, Frank Wagner, so he used a different method, but based on what Oshensky did for the Burnside group. In his method, you can actually embed the free Burnside group into a finite presented group with quadratic Дэna function. So that's very interesting because there are many results regarding what's the common properties of groups with quadratic Дэna function, except they have the quadratic Дэna function. One of the conjecture is, okay, they should not have torsion subgroup, the infinite torsion subgroup, of course, because for the hyperbolic groups, groups do not have a infinite torsion subgroup, but it's not conjecture if that's also work for the quadratic Дэna function, the groups with quadratic Дэna function. But then this is a example that group with quadratic function can have a infinite torsion subgroup. Okay, so that's for the Burnside variety. Okay, for the second, so this is part A. The last one I have to mention today is about the solvable variety. As a result of Kleiman, you have a variety there exists a solvable, some variety that's basically so with non-recursive verbal isoparametric function. So they basically he construct a variety such that you cannot decide if any word is produced by the identities defined the variety. So the non-recursive verbal isoparametric function. Okay. Or also you can replace the isoparametric function by Дэна function. Okay, so I think that's all I have to say today. Thanks for your attention. Yeah.
So, Vенхао, other questions? Okay, there's some.
Maybe I have a question, Igor. Maybe that's a question that I should address to you.
Okay.
And it was about the word problem in the free Burnset group. So it was said that according to one of the theorems, it's in NP, but ain't it in also in the class P?
Okay.
The conjugacy problem.
I was thinking about this for about 3 minutes during the talk, so I don't know the answer.
Okay.
NP?
No, it is. Is there a polynomial time algorithm to solve the problem for Burnset groups? I don't know actually. It's an interesting question.
Okay. So it's still unknown if this word problem is in P, right?
Yes, it's not known. Okay.
Okay.
But it's a good question. I will try to maybe I could answer. I don't know. Okay. So actually, okay, this talk was not so long, but it was very informative. So thank you, Vенхао, for this informative talk.
Thank you.
Okay, no questions. Okay, no questions. Okay, so this is all for today.